Okay, so we're recording. Welcome, everybody. This is Joe Armstrong, and we are at the Power Systems Virtual User Group webinar for August. Getting close to the end of the summer here. I hope everybody's had a really good summer. I have just one thing I want to talk about today before we get started, and that is my usual plug for the IBM Tech U conference in Las Vegas this year. So IBM puts on a couple, usually two. They kind of varied over many years here, but usually two tech conferences a year. IBM Tech U, they call it. And this next one is October 7th to 11th in Las Vegas. And these conferences, I think, are the best conferences that IBM puts on, especially for technical people. Maybe if you're a CEO or something, they have something better. But for this, for the people that we get on these webinars, this is the best conference. Just loads and loads of sessions to go to from really great speakers, IBMers, non-IBMers that are champions in their field, like some people that we have on here, and just great speakers. So if you can go, I encourage you to do that. And if you do go, let me know. And I'd like to hook up with you while you're there. So I also have a promotion code here. So if you are going to go, this TUVUG code right here will get you a discount price on it to this $20.95, which I think is a super early bird price. So you get a little bit discount here with that code. So feel free to use that code. It's good all the way up to the conference. And when you register, you can put down my name as the IBM rep. I told you about the conference, and then hopefully I can get there too. So also, if you're in Chicago, there's a Chicagoland Technology Day next week in Schaumburg, Illinois. I'll be there. There's no charge for this. It's a day of some kind of minor sessions, really good stuff that they're going to talk about there. So if you're in the Chicago area, you can go to that. And on the wiki, there's a link to the flyer here for you to go to. So with that, let's get to today's here. And so I'm going to stop sharing. And Earl, I'm just going to make you the presenter so you can get going. And while you're getting that set up, I will introduce you. So today we're going to talk about considerations and strategies for POWER9 workloads. And every chip is a little bit different that IBM puts out. It has different features, the way they do things internally. And sometimes that makes a difference in how you tweak your system. So, and actually, it kind of helps you to tune your system if you know how the chip works. And so we've got today Earl Jew here. Earl is with IBM Lab Services. He is a master at what happens deep in the processor chip, how to read tuning numbers, and we've had Earl on before to talk about tuning strategies and stuff. So today, Earl's going to tell us about the POWER9 chip, how it's different, and how to change your workload, how to tune it to work best in this environment. And I'm just going to give you a heads up here. Earl gets really deep. He gets really technical, and there's a lot of information that's going to be coming. So get ready to absorb a lot and get ready to go deep with Earl. So with that, Earl, I'm going to turn it over to you.
Thank you, Joe. And we have Tom Prokop. Hopefully he'll unmute and jump in now and then when I ask, as well as you, Joe. I'm going to need you and your background. I believe you used to design CPU chips or something like that?
No, I just wrote software for them.
Oh, okay. Very good. Systems programming. Today I have a title you may be familiar with from my last two Tech U's. Though the title may be the same, I keep changing, enhancing, maybe improving my presentations. These are 7 sessions. I'm going to be speaking these same sessions in Las Vegas and Sydney and maybe Prague too. The numbers will change and the content within will also change, though the same names are there. So we're starting here at the second of 7, the white paper. Well, I can send that to you if you want. This is a quote directly from that white paper on the bottom. Talks about the processor, and for AIX, we only run on the 12-core variant. not the 24-core SMT4 variant, but the 12-core SMT8 variant. And this whole chip here is called the processor. And throughout this presentation, I'm going to call that processor an SRAD. So this is an SRAD, Scheduled Resource Affinity Domain. It's a hardware chip, wafer, socket, whatever you want to call it. Okay. What to know? We're going to go deep into a particular number that so far only I seem to look at. And we're going to learn about ERAT, TLBs, HPTs, and address translation faults. So what to know, the usual format, how to see it, then do this. Different topics today. We're going to learn about effective to real address translation, ERAT. And we're going to trace the events of virtual to physical memory address translation faults. It sounds miserable, but we're going to go through it a few times. Also for note, I arbitrarily call large processes 6 to 8 digits in kilobytes, RSS, resident set size, and small processes are 3 to 5 digits kilobytes, and huge processes are 9 digits and larger. Okay, so that's just how I categorize them. We're going to talk about this number, VMstat-S, address translation faults. That number is what I call making it real. Whenever AIX needs memory to create a process, or to read data through the cache, or to write data through the cache, there's a proportion, I said proportion, of address translation faults. It's not one-to-one for everything. They go in ranges. Faults are how AIX maps virtual addresses, also known as effective addresses, to physical memory on DIMMs. This is what I mean by making it real. AIX, because it's a virtual memory operating system, thinks in virtual addresses, the hardware thinks in real addresses, and then there's translations from virtual to real. These translations are what I call pointers or page table entries in the translation look-aside buffer hardware page table. So these are structures in the on the hardware. This is memory in the hardware. Okay? So we're going to talk about that number and how it dissects down. Key point. This count and scale of the number is AIX memory used for creating processes or moving I/O through what I call VMM-initiated I/O. That means I/O needing free memory. I/O going through AIX free memory, not JFS2 concurrent I/O, not Oracle ASM, not GPFS, not raw I/O. This is JFS2, default I/O. This is a slide that you'll find in the PDF. You won't see all these ghosts of signs here. Now here's a key question. Which of the above applies to POWER8 and POWER9? I think we all know this answer. AIX uses 64-bit addresses, and that big number, 16 exabytes of memory. That's a lot of memory that it can directly address. But the largest E980 only can house, well, I'm making a joke here, it can house as much as 64 terabytes. So we know that 64 terabytes is nothing compared to 16 exabytes. Here comes the key question. How can AIX address 16 exabytes if there's only 64 terabytes, especially if there's more than one LPAR on a big E980? Of course, most of our machines are much smaller. Okay, you caught me. This 64-bit address is uniquely maps 16 exabytes of virtual memory. Not hard DIMMs, virtual memory. And this is what we need and how we need to think. AIX imagines it has access to that much memory, and it just leaves the rest of making it real to the hypervisor and the hardware architecture to resolve. So AIX just merely goes and believes it has all this memory. We don't actually reach 16 exabytes yet. But we can raise that high, which is why we'll probably never have a 128-bit address machine, because that's already very big. So AIX imagines and leaves it to the hardware to make it real. The gist is simple. Virtual memory mapped to real. That's what we're trying to do. Technically, AIX assumes a simple linear range of logically effective addresses, that's this here, EA, that are converted to virtual addresses by the CPU. Before translation in the memory management unit, every core has an MMU, this is hardware, translation to physical addresses, real addresses. So AIX plays here, and it goes translation to physical memory I/O devices. This is how I/O comes through here. So it goes this way and this way and this way and this way. This whole transition is called an ERAT, effective to real. This is what I mean by making it real. Okay? This is occurring all the time. This is always going through here and hitting there, back and forth, through every core, discretely, independently of every other core. 16 exabytes of virtual memory are effective addresses, logical addresses. This is the imaginary memory, and that's what these addresses are. Now, the inner workings of the MMU is where the TLB and the HPT reside, and we need to explore that. So we're going to expand this scope in orange lines here on the next slide. There it is, memory management unit. Every core has a memory management unit embedded in it. And next to the memory management unit is the TLB, the translation look-aside buffer. Think of this as just a cache of these virtual to address translations. This is just a pointer with an LPAR ID for each pointer. There's a cache of 2,048 of these in POWER9, and there's a cache of 2,048 of these translation entries in POWER9. On POWER7, the same counterpart TLB had only 512 translation entries in each core's TLB. So here's a TLB, and the virtual address goes in, scans his table. If there's a hit, there's an immediate next access of physical memory I/O device, okay? These entries are called PTEs. So in the TLB, they're PTEs. As I said, almost all virtual addresses go into the TLB and scans it. Now, this is very fast in hardware, and almost all of them are hits. If there's a hit, you hit main memory next very quickly. This occurs almost always because it happens so fast. This is the map to the hardware. Okay, this is how we map the hardware. This virtual address maps to the hardware. Okay? Goes back and forth very quickly. The problem is that sometimes you miss. That means the address entry is looking for isn't in here. It's either a new virtual address or it was flushed out of the TLB. So a TLB miss walks to hardware page table hash table, and it walks main memory. Now, the hardware page table is a master list of all the valid PTEs in physical memory, meaning here you want to hit main memory quickly for what you want when you have a hit, but now you have to do an HPT walk to find a hit. Most of these are hits because they're existing. When it hits, the references are then now transferred and put in the TLB, so the next time it won't have to walk the HPT. Our focus, though, are the misses. When you miss in the HPT, it's because, by the way, if you miss an HPT, it's called the address translation fault. We wonder why it's called a fault. A fault means it missed walking this hardware page table. These misses are new virtual addresses needing physical addresses to real memory. That's what a fault is. It's making it real in real memory. Okay? That's what we're focused on now. Same words. Making it real. From above, AIX imagines 16 exabytes of virtual addresses, and the hardware makes it real. From above, simple linear range of effective addresses translates to virtual, then translates to physical. That's called an ERAT. Effective addresses are virtual memory. Why do we have new virtual addresses needing assignment to real memory? Well, pretty easy. You create a process. When you create a process, you got to make it real. It doesn't run otherwise. When processes are created, there are faults. Allocating real memory to new virtual addresses of a simple range of effective addresses representing each process. And here's the crux of it. Creating huge, large processes suffers many more faults than creating small processes. In the original small operating system on 32-bit, I guess where AIX was born, all the processes were small because the memories were so small. Well, today's memories are big, and so are the size of our processes. Large processes suffer many more faults in their creation. We have a new scale. And unlike old thinking, creating processes is often a substantial workload. What I'm doing is opening dimension and realization that, well, let's see if you guys can answer this question. How fast can a process run if you don't have the free memory to create the process? That's an issue. If you can't create the process, it doesn't run. So if we have large processes, we have to make sure there's enough free memory in fewer memory pools so that the process can be created and begins to run. Whole new way of looking at it. Processes are getting bigger. I just started seeing my first set of huge processes at 9 digits in kilobytes. Why else do we need new virtual addresses? For data. After you create a process, now every time you move data through, you need to have these faults. So this number here is address translation faults, and it's the scale of all memory used. From my experience observing this number, I have this legend. Some of you may have seen this legend before. This is the scale of memory used. And you can see I set it at 90 days. I guess it's easy to explain that if you just booted this system 5 minutes ago, all these numbers are going to be pretty small. Here, it's 10 days. I set it at 90 days, and since it's only 10 days, I take a 9-digit number and divide by 9, because it's only 90 days up. What I mean is I scale it to a standard of 90 days. And here at 10 days, this 11-digit number, in 10 days, it calculates out to a 12-digit number at 90 days. Meaning Mr. Ed and his workload is a rare, frequently large memory demand of a workload. This is how I scale the memory demand of the various workloads I tune. Apple Computers iTunes America is pretty big. That's 13 digits. 14 digits, I've never seen it before. Where do you fall on the scale? Remember, you scale to the day's uptime. This is Mr. Ed. This is Wilbur. Wilbur's up only 1 day, and that's 11 digits. This is huge. This digit count is an indicator of scale of memory used, not CPU processing. And this count is certain and reliable, yet no capacity management tool is considered using this number. I believe that's a fault. That's why I'm making this presentation. The scale of memory used can be small to something vastly huge at 12 digits, and only twice have I seen 13 digits. About a month ago when I was in Australia, I met my second 13-digit number in 90 days, and I was stunned. Advice. Compare your faults on familiar workloads with your less familiar workloads in preparation for designing your future LPARs by the principles of assumed scale of design. These principles are in an earlier presentation. I'll send it to you if you write to me. This third principle says that the higher the digit count of that number, The more memory you need, more CPUs you need, the faster I/O data structure, infrastructure you need if you care for a piece of performance. Why? If you're using big memory, you better be able to feed that big memory. For instance, say you have 50 terabytes of data and 4 gigabytes of physical DIMMs RAM. If you're trying to work with that much data in a day, 50 terabytes of read-writes in a day, and your memory is too small, all you're going to do is I/O all the time. If you've got 50 terabytes of data that you read and write in a day is what I call accessed data. My definition, I make this stuff up, I'll call it what I want. Accessed data is the amount of data that you read and write in a day. If you're reading and writing 50 terabytes, it's kind of nice to have 2, 3, 4, 5 terabytes of RAM to reduce the data rereads. And when you read the data in, flush it out, read it in, flush it out, the more memory you have, the less you do data rereads. So, as our data gets bigger and our LPARs get bigger, we have to scale up with a larger amount of memory for more access data. Okay, on to power tuning. This is kind of like hardware tuning. We all are doing AIX tuning. Power tuning is about how your LPAR is manifested on the hardware. The LPAR is virtualization and affinity on the hardware. Okay? The whole point of this is what I'm trying to do when I tune. Strategically, eliminating avoidable workload. Not doing something avoidable, always faster than doing it. What we're really doing is reducing the path links of operations. It's always faster and more efficient. Careful selection, thoughtful configuration of the LPAR will substantially reduce traffic between components. Traffic between components inside and on a hardware is a longer path than traffic within the component. The fewer components you have and the more you contain traffic within fewer components, the shorter is the pathing of all operations. So there's an aspect of tuning that nobody seems to talk about but me. Buy and build to eliminate and reduce the latencies of avoidable inter-SRAD, inter-cache coherence. We're going to talk about cache coherence, as well as L3 cache accesses, thread migrations, which are very different from virtual CPU migrations, DIMM accesses, and PCIe traffic. We're going to talk about all 5. Not only going to talk about it, I'm going to illustrate them. Here they are. And as scary as all these sound, it all comes down to a simple meme: squeeze harder. The whole point of this presentation is to get all of you to push your LPARs into as few SRADs as possible. Ideally, you can boot your LPAR on one SRAD without pieces of your LPAR across multiple SRADs. Why? To reduce the inter-SRAD traffic, what we call affinity. Squeeze harder. 3 scopes of cache coherence. Power 7, 2 scopes, KEC only. Power 8 introduced 3, and now Power 9, we have 3 scopes, but we added vectoring between KECs. Don't let it scare you. We're going to see what it looks like. Okay? So Power 9 continues with 3 KECs. 3 scopes of cache coherence. There's a KEC. This is also what an E950 looks like, all by its lonesome on one board. What is cache coherence? Take your time to read that. The latest value of anything in both RAM and cache is always perfectly consistent. That means we may have a value in RAM that might be in multiple caches or multiple cores, and the hardware absolutely guarantees that the most updated version of that value is consistent everywhere. It resolves this extremely quickly by dedicated hardware logic, cache coherence. Okay? It's a guarantee by the hardware. The OS doesn't have anything to do with it. POWER9 continues with SRAD only cache coherence, meaning if you boot your LPAR on one, any of these cores of your LPAR never has to sniff the cache anywhere else in a coherent scope. It only runs within it. Now, other scopes of cache coherence are very fast, but still, not doing something is faster than doing it. Next wider scope, the whole keck. And then we have everything on the next slide. This is everything. This red thing is that one right there. This is E980 fully blown. One keck, one keck, one keck, one keck, 4 SRADs each. This is the widest scope with vectoring between kecks. POWER9 continues, cache only, SRAD only cache coherence. And if your LPAR is booted on one LPAR, to the tightest scope of coherence, shortest coherence path lengths, this is very fast. And I mean very fast. Because you don't have to coordinate traffic with other SRADs. As well, given that we have as many as 12 cores, and each core is denser and deeper, more execution pipelines in the core, deeper, we can hold more instructions in the core. A larger concurrent scale workload can more easily fit in one SRAD. This is a flattening of the architecture. The more power you have in one SRAD, the less interaction you have to go anywhere. That's what I mean by a largest concurrent scale of workload. What is this? What do I mean when I say the concurrent scale of workload? How do we know in C the concurrent scale of workload? And the big question, should we be tuning by the concurrent scale of workload? Well, I'll tell you what I do. I use a 1-minute average. The concurrent scale of workload is a 1-minute average of KTHRR. Now, this KTHRR should be pretty familiar because last November I did a whole 90-minute webinar describing what that is. So you take that number, average over 60 seconds, you probably know the number better as load average. Uptime, load average. I use uptime mainly to get the day's uptime, but this load average here is most recent 60 seconds value 5 minutes ago, and the 60-second average over 1 minute 15 minutes ago. Those load average numbers define the concurrent scale of workload over 1 minute. Now, I know I've been teaching all of you to monitor at 1-second intervals, but when it comes to the concurrent scale of workload, I'm saying take the 1-minute average, which is still a tighter timeline than most of our capacity management tools use. Should we be tuning by the concurrent scale of workload? Yes. Here's the problem I'm finding. You may only need 28 logical CPUs. 28 logical CPUs is 7 virtual CPUs SMT4. And what do people configure? They configure 16. There's 24 of them. This is a real problem. This is why I'm teaching this technique. Say we monitored load average for a month. You know, you put it in cron. And over that 1 month, the highest ever reached in a whole month is 27.96 right there. With the max month load average fits safely in 32 logicals. That's 4 virtual CPUs SMT8. 32, yeah. Well, I think it would. Very easily, actually, if that's the max. Would it fit safely in 28 logicals of 7 virtual CPUs SMT4? Yeah. In fact, I believe you can get 2 of the same workload on 4 virtuals SMT8 on the same SRAD, with the difference only being SMT4. 4 versus SMT8. With 32 logicals, 4 virtuals SMT8 fit nicely on a POWER9 SRAD 8-course SMT8. I think so, yeah. 28 logicals, 8 SMT4. Yeah. All those answers are yes, and I just showed you how I size the concurrent scale of workload. The next wider scope is KEC only. By definition, if and only if the concurrent scale of workload that I showed you how to do above here is greater than 1 SRAD, if it's greater than 1 SRAD, then it would desire more than 1 SRAD in the LPAR configuration. Guys, if you've got 12-course SMT8 on 1 SRAD, you've got to be one huge concurrent scale of workload to be larger than an SRAD. I don't count add very well, but just say it's 8 cores times SMT8 on 64 cores. All right, 64. If you have a concurrent scale workload at 64 and higher, that's actually bigger than easily 4/5 of you out there. That's when you need a second SRAD. LPARs booted on more than SRADs suffer more inter-SRAD traffic. No one talks about it, but it's there. Thus, strive to boot on the fewest SRADs to contain the concurrent scale of workload. Just showed you the technique. And this is how SMT8 cores are, to me, most helpful. By exploiting SMT8, you can get a larger concurrent scale workload and more of them on fewer SRADs, if not 1 SRAD, simply to reduce the traffic between SRADs. Wider scope is everything with vectoring between KECs. These are freaking huge LPARs. Not many of them. Requires SRADs are more than 1 KEC. And here's the goofiness. Some are within our control. We can control this, actually, by how we LPM and using DPO, the order we boot our LPARs. Many ways we can control this, but sometimes they're scattered. That means you get 2 up here and then 1 down here. Well, that's not good. You want all 3 on the same KEC if you're that big. This is POWER9 E880. When this same kind of scattering of SRAD assignments occurs on a POWER9 E880, the scope of cache coherence checks every core on every SRAD, which is a lot greater scope of checking other cache for a cache coherence algorithm in hardware. There's more latencies. When we do this, when we find it scattered like this on an E980, we substantially narrow cache checking by specific vectoring, meaning these 2 SRADs only checks that one, and this SRAD only checks the other 2 and doesn't sniff all the others on the hardware. So we moved from this to this for a reason. The engineers wouldn't have done it for a reason. This is a lot faster, of course. That's why we did it. On to others. The different kinds of cache accesses and cloning. I stole this from the paper, this quote here. Okay? You see the L3 caches, as many as 12 of them, and each has its own region, 20 ways, set associative, with advanced replacement policies, meaning content in the L3 cache on POWER9 replaced content in the L3 cache by least recently used LRU algorithm. Today on POWER9, we're using advanced replacement policies, meaning they are today heuristic in what we toss out when we bring in new cache content. Not only do we have all this cache on the SRAD, but we have a fast fabric to communicate between each L3 region. This is key. Suppose you're running on this core, you got content in L3 cache. Well, you find that maybe it's not in this L3 cache that you're trying to access, it's over here. So you transfer your L3 cache access to a fast fabric. Not only that, but threads running here may have to migrate to another core. You migrate the data instructions of that through the fast fabric to another core. Next, we have cloning. We'll talk about that, cloning. The on-chip L3 cache has different latency characteristics. That means some is faster and some is slower to access. We'll show you how. Okay? Every core has got its local L3, but also has access to all the others. We'll see this. Additionally, we can access those other cores, depending on that parameters, and we can clone. So I'm going to illustrate what this looks like. This I stole from the Red Book. We know what that is. And quote from right above, every core, or this is SMT8 cores, two SMT4 cores fused to make an SMT8 core, has its own local 10 megabytes. This is the fastest access this core can have to this local cache. But also, this core can access the cache of all the other cores. This is an L3 cache shared region here. Okay? It can access it by negotiating it. That means this is fast, accessing this a little slower. I call this consideration sibling cache accesses within an SRAD. The more active cores you have on an SRAD, the more L3 cache you have on that SRAD, the more easily accesses, migrations, and cloning could occur, and the larger LPAR you can put on one SRAD altogether. Sibling cache accesses. Data can also be cloned. That means the data was here, it got copied to the local L3 cache here, and now you got two copies of it. Why? This accessing this local copy is faster than having to transfer it. That's why it moves it local. So you may have multiple copies, depending on reference patterns, of the same data in multiple L3 caches. This is single SRAD L3 cache cloning. Well, now we got two SRADs in the same LPAR, multi-SRAD LPAR. That's what I want you to see this as. And I call this cache accesses between SRADs. This is the nature of NUCA, non-uniform cache access. It accesses its own local, it can access sibling, and it can access on other SRADs, and it can access L3 on other SRADs on other CACs. There's a hierarchy. That's what it's meant by non-uniform cache access, or non-uniform cache architecture. Cache access between SRADs. Now, we know that on the chip, the L3 has got different latencies. What would you expect the latencies to be between SRADs on cache accesses? Of course, accessing the L3 cache on another SRAD would have longer latencies. Not doing that is faster. We also have multi-SRAD L3 cache cloning. Let's think about what cloning is here. Multi-SRAD cache cloning is an inter-SRAD L3 access, transfer, and write to another L3. That's quite an operation. Everything goes on that fabric for accesses, for cloning, as well as migrations, and of course accessing DIMMs goes through L3. That's why that 7 terabyte combined on-chip fabric is so important, how fast that is. Okay, migrations, DIMM accesses. In the MPStat syntax, we'll see this later, migrations of threads among logical CPUs of AIX. Of course, logical CPUs are assigned by this map, LSSRAD. So our threads migrate among logical CPUs. Virtual CPU migrations. What? Virtual CPUs migrate among cores. But when a virtual CPU is on a core, that's the only time logical CPUs can appear. In a shared processor LPAR, a virtual CPU must be on a core for the logical CPUs to be available to the AIX reality. So, virtual CPUs are migrating among cores, and logical CPUs are migrating among the logical CPUs as virtual CPUs are migrating among cores. This is maddening, but true. Most virtual CPU migrations occur when you're running beyond entitlement. The other way it occurs is when you configure more virtual CPUs than the count of active cores on an SRAD. Say you have 8 active cores on your SRAD. I have customers that assign 20 virtual CPUs to a socket with 8 cores. The only way you get 20 to fit on 8 is you migrate them around on 8. So you add all this hypervisor overhead. There is nothing gained from 20 virtual CPUs on a socket with 8 cores. All you do is you up the hypervisor overhead and do more of these virtual CPU migrations. Now, not doing them is faster. Uh-oh. Virtual CPU migrations cannot be directly monitored. No wonder this concept is not in our tuning lexicon. If you can't see it happening, of course it's not happening, right? Well, I don't think IBM's amused with me telling you this, but you already know it intuitively, what I'm telling you. And then dim accesses. Under MPStat, we show you the percentage of dim accesses. Percentages are good. But I hate to criticize my company. Give me a percentage, thank you very much. But a percentage is only useful if you know the volume. 100% of 1 is real different from 20% of a million. Okay? So I don't see the count of dim accesses, but we give you percentages. Thank you very much. All right? So we're going to talk about these. Same words. And there's an SRAD. Key point to remember, right there. Instructions and data of executing threads must be in L1 instruction cache and L1 data cache, or that thread can't be executing. By the rules of the documentation, if the instruction and data are not in the cache L1, that thread's not executing. It won't begin executing until it gets there. And the L2 feeds the L1 caches. So, when we're migrating threads, this is what we're lifting and migrating. If it's executing and migrates for execution, it's lifting instructions and data and moving it somewhere else. L2 feeds L1. Most threads return to execute on the same core. This is a migration to nowhere. It ran here before, next interval, it didn't move anywhere and ran there again, meaning the cache stays right where it is, migrations to nowhere. These are S0RD, S1RD migrations. They are perfect. This happens more than 90% of the time. Some migrations migrate between cores. So what was here got migrated over the fast interconnect to the other L3. These are considered acceptable. If you can run on one socket, you keep all of your migrations to this. Other go off the socket. A smaller subset goes off the socket if and only if you have a multi-SRAD LPAR. Tuning considerations aim to reduce incidence of migrations between SRADs. This is the map. Ref10 is a KEK. Ref11 is another KEK. SRAD. That's why I use the word SRAD, because it means a chip. This chip, S0, SRAD 0, has local DIMMs. Local DIMMs, local DIMMs, local DIMMs. So this is the map of AIX on the hardware. And these are virtual CPUs, or I should say logical CPUs, assigned to the SRAD. What is missing here is again, I hate to criticize, but I have to say it. We have no way of identifying the active core count per SRAD. You don't know if you've got 10 there, cores active, 8 cores active, 12 cores active. Of course, if you bought 12 cores and you turn on everything, now it's easier because you know they're all active. But because of COD, DIMMs, COD cores, because of Power Enterprise pools, because of mobile activations, that count of active cores per SRAD is variable, and I don't know what to do about it. But since we can't show you, or we don't show you the count of active cores, how do you know if you got the right count of virtual CPUs on an SRAD? I used to use Power VP on Power 8 to make that determination for me. Power VP was not ported to POWER9, and I'm not amused by it. So now I'm lost. I don't know what to do. So you got that problem too. Local DIMMs. We got the percentage of DIMM accesses, and this illustrates this SRAD accessing its local DIMMs. These 8 channels are not interleaved. They're all discrete and independent from one another. These are the S3 HRD under HP stat. These are local DIMM accesses. They're perfect. More than 90% of your DIMM accesses are going to be local. Please see this as 2 KEKs, 4 SRADs each KEK. And let's talk about near-far DIMM accesses. When this SRAD accesses those DIMMs, the DIMMs on the same KEK of another SRAD, it must do so by an SRAD to near SRAD request. Obviously, that's a longer path. These are the S4 HRD under MP stat. Again, when this SRAD accesses the DIMMs on another SRAD on another KEK, it's got to do it by SRAD to far SRAD request, an even longer path. I told you we'd talk about power tuning. Joe, I'm not going to finish it today.
Well, you get through what you get through.
I'll get through what I get through, yeah.
And we can schedule you up again.
Oh, I don't know if they can stand that. They aim to reduce.
Are you trying to get in one of your 4-day sessions in 1 hour?
Yeah, that's what I try to do all the time, Tom. Earlier presentations, I almost ran out of content. I made sure.
Yeah, I've been in your 4-day sessions. My ears bleed.
Here's Edard. This is a shared SMT8, POWER9, half a terabyte of RAM. This is a big LPAR. And we see how the map is, okay? These are migrations, and the run queues, not important. This is about local processor affinity. That means if this number is less than 100, you got inter-SRAD traffic, and that's what that says, off inter-SRAD traffic. Under MPStat-W, this is MPStat-D. This shows you where the migrations went to. So these are the perfect ones. S0, S1s are perfect. S1s is just moving between the logical CPUs, same core. S2s don't exist. S3s are acceptable because they're inside the SRAD, and those go between SRADs. So now we got a map onto MPStat-D. These are the DIMM accesses and the percentages. We see how it maps. What I defined above maps to tactically to MPStat-D. Here's a good one. This is Jamie, a different LPAR. Virtual CPU migrations occur when executing beyond entitlement. So this is why we don't want you to run beyond entitlement for performance priority workloads. Okay? Running beyond entitlement doesn't break, it runs. And if you don't need the performance, go ahead and run over entitlement. But also, virtual CPU migrations occur when you configure more virtual CPUs than the count of active cores. And we know that that is 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. How well does 21 SMT8 virtual CPUs, logical CPUs total count, run on a socket with 8 cores? All you do is you up the hypervisor's overhead trying to do all that virtualization. Well, How many of you guys are monitoring the hypervisor? When you build an LPAR like this and it runs slow, you don't see it in AIX. This particular customer was not amused when I showed them that the fault for their performance was what they did to themselves. I had to show them how to correct it. Virtual CPUs migrate, cannot be directly monitored. Key concept. At least I got this one in today. RRR, ratio raw resources. Every POWER8, POWER9 is comprised of SRADs. We got it. Typically, every SRAD's got activated DIMMs and activated cores. Unless somebody did something really wrong, every SRAD's got activated cores and activated DIMMs. Ideally, and this is a really high ideal, they're all identical activations of the same amount of DIMMs, the same amount of activated cores. That's ideal. That's kind of rare these days. So when I say every SRAD could have a unique DIMM to core ratio. Now the concept is sound. Uncovering what you really have is kind of tough, but I still got to give the concept. So say your DIMM to core ratio per SRAD is all 32 gigabytes DIMMs per core. It could be different because of the CODs and power price pool mobile activations, and it could vary throughout the day depending on how active that is. No matter, we have ignored our RR per SRAD when we've been building our LPARs since Power 4 on to today. We need to be aware of the RRR, and if you build out of alignment of the RRR, you're going to boot with more SRADs in the LPAR. So now I stay at the problem, I'm trying to give you the solution. This lack of awareness compromises performance and efficiency. The answer is align the LPAR to the ratio of DIMMs to cores on the hardware. How much memory you've got per DIMM set? How many active cores you got per SRAD? I don't know what to say. Say it all over again. That SRAD in blue has got these cores to these DIMMs. It may have its own ratio. There may be two different ratios between the two SRADs, and we've ignored these different ratios, and what happens? We may end up booting an LPAR with more SRADs because we're not booting an LPAR in alignment with the ratio of raw resources. Say you've got a new E950, 2 terabytes, 40 cores, and ideally you turned on everything. Everything's activated, ideally. Now your RR is 51.2 gigs per core. Okay. Well, we're going to apply it. When you apply the RRR calculation to any dedicated CPU LPAR, it is brutally simple. You can't miss. Applying it to an SP LPAR is akin to reckoning the Higgs boson. You see this sad face here? I don't know how to do it. Sorry. I come up with a concept. I don't know how to do it to a shared processor LPAR. When you try, you'll understand, all right? If you confidently know it's 51.2 gig DIMMs per core, do not configure too much more than that ratio, or you're going to boot with more SRADs on reboot. Do not configure too much less than the ratio, or you're going to boot with more SRADs. You're going to have to think through how that is true. Don't want to explain it here. But that's how the rule is applied. Now, I'm going to offer the concept, but applying it to shared processor LPARs, I leave to your greater ingenuity, and when you figure it out, you will teach me, please. PCI slot locality placement of HBAs and NICs. This topic of where you put these cards relative to which SRAD is running the LPAR aims to reduce the latencies of device interrupts across longer path routes between the two. Meaning, where you put this and what you assign to where, that's what this is about. This is managed by the affinity group number feature at the command line interface Most of this is done properly for you by the HMC. If and only if you don't stuff all the 10 gig keys in the same bus, you know, spread them around a little or a lot. I don't build anymore. I used to build LPARs, but Lab Services only makes me do performance tuning anymore for some reason. But at least I can illustrate what I mean. That's direct and ideal. What am I saying? This PCI slot goes straight to the SRAD that's using it. One VIOS, another VIOS. That's indirect and is acceptable. If you've got an E950 or a smaller, you can't miss. You're going to be one or the other. What you don't want on an E980 is that. I don't think I need to explain that. Everything I'm telling you is to try to get you to realize that power tuning is about squeezing your LPAR down to as few SRADs as possible, being that the POWER9 SRAD SMT8 course is so powerful for so many concurrent threads, you can boot a large LPAR on one SRAD. It's a flattening of the architecture. Iron build to avoid inter-SRAD traffic and those 5 aspects of it. Thoughtful configuration, substantially reduce traffic between LPARs, between components, that is. And not doing something avoidable is always faster. I call this power tuning. And I'm going to finish. Strategies. Then do this. I love ARIA. Strategy. We got 4 strategies. Joe?
What?
Dude.
Yeah,
Are there any strategies for how to build and mix and match LPARs on our power servers?
We definitely have, you know, when you were talking about where to put in your PCI cards and stuff, there's PCI slot. You know, this is how you should put them in the slots and such for that. There's documentation on that.
Yep. But what I'm talking about is overall strategies governing how an architect would place, mix, and match workloads and LPARs on the same frame. My philosophy is understand the workload, understand the hardware, and then build the right LPAR for that workload. That's what I That's how I do it. Oh, yeah. What do people do? They build in the LPAR, put the workload on there, it runs, touchdown, you're done. The trouble is the LPAR they built is not built to be optimally running the workload that it's got. We've been doing it backwards is what I'm saying. We don't have a strategy for that, which is what these 4 strategies are about. How do you know what size LPAR to build for this workload? Isn't it better to know the workload before you build the LPAR? That way you build the right LPAR. You don't build any LPAR, but that's what we do. So that's what these are about. I don't believe I've ever found any strategies with regard to that, so I had to conjure my own. So
it's mostly built around experiences I've seen, Earl. I mean, you have the people who are building the LPARs that understand the workload because they've been working with them, and it's all built into experience right now.
Well, I'm going to give them something more structured so they can throw darts at. So, strategy, a frame level perspective whereby a few LPARs has the highest requirement for exceptional performance. These are what I call Black Friday, OLTP, high transaction workload LPARs, stock trading and such. Okay? Highest requirement for exceptional performance. And then most LPARs are essential production but don't have such a high requirement performance. Those LPARs in the dark blue are what I call manic depressive bipolar workloads. They're very busy when they're busy, and when they're not doing anything. And then all remaining LPARs can otherwise tolerate running whatever's available. These are non-production LPARs. Note the colors. I say a frame level perspective strategy implements a proper mix of all 3 above. A proper mix, not an equal mix. A proper mix on your priorities. Based on the RRR. Well, somebody talked about RRs already, huh? This optimizes the 12-core variant of SMT8 cores. Rationale, avoiding longer path overhead is always faster. Right? I hope you guys all like this slide. These are the 9 ways that I would build an LPAR on POWER9. Assume hard SMT8 for all below. This is the highest performance. This is production, essential production, and this here is your non-production. You need to choose which one of these you choose to implement. And, of course, I have all kinds of content talking about this. What's the difference going from top to bottom? Continuity to greater discontinuity. This talks about CPU virtualization of virtual CPUs on a core. When you're more continuous, you're going to run really fast, but very wastefully, when you don't have a fully blown workload. Down here, you're not going to run so fast, but it is using every little bit that you've got. Continuity, discontinuity. And those 5 LPARs configurations are special. Why? If you boot it this style, you can, without rebooting, scale it down here in green, or go up and down. What I'm saying is you can add and remove entitlement. You can change the virtual CPU count. You can turn on or off folding, and you can change the VPM throughput mode. And what I've just done is added a few more tools in your toolbox. By comparison, I believe everyone's got a hammer in their toolbox. But if you've only got a hammer in your toolbox, everything looks like a nail. So I've given you a few more tools here. And I say you should start building your POWER9 LPARs unless they're OLTP high performance requirement, that you should begin POWER9 LPARs right there in the middle. I have a whole lecture on why, and I'll get into that. I got PowerPoints on it. Another strategy. This is pretty easy. OLTP, batch, and some LPARs do them both. They either intermix or switch both workloads. This here strategy requires knowing the history priorities of the LPAR. New LPARs are like young vampires. They're unpredictable. They can go crazy. I'm sorry, I got dragged to those movies. And so for young vampires, young workloads, you have to have ready access to on-demand resources. It means a higher memory max and a higher count of virtual CPUs. Not desired, but a higher count max. Old workloads, old vampires, history remedies, they're calm, they're stable, and if they've gone wrong in the last 5 years, you already figured out and fixed it. So you hardly need to have urgent resources, and most LPARs, 2 to 3 years of service, they fall in between. So considering the workload's history and its priorities and how you intermix them on the same server, that's what I call a strategy, and review the history. Isolation versus spread of intensity, third strategy. Running threads dense and deep on fewer CPUs is what our SP LPARs try to do, our shared processor LPARs. And if you care to run denser and deeper on fewer virtuals, that's what mode 2, 4, and 8 does. Every time you move it from 0 to 2 to 4 to 8, you increase the isolation of intensity to fewer virtual CPUs. Isolation intensity is a CPU efficiency mechanism of shared processor LPARs on the Power hypervisor, Power VM. Versus that, we have spread of intensity. When you boot in a dedicated CPU LPAR fashion, you spread your threads evenly across all virtuals, all cores. This is the default behavior of dedicated CPU LPARs. Building an LPAR like this spreads the intensity, and the only time this is justified in my book is if you have a high need for extreme performance of OLTP transactions, and you have a volatile run queue of those transactions. Build a dedicated, only that. Running dense and deep, a denser, deeper core can do more work because there are more execution pipelines. In the POWER9 core, we've got more than twice as many working engines versus POWER8 in the core itself. So the core can do more work. I call that denser. Deeper. The core more than doubled how many instructions you can hold in the core. Now, this causes me a problem at monitoring. Well, when you hold more core instructions, you never empty the instruction buffer inside the core. That's what I call deeper. We have denser, deeper cores. Fatter, flatter. Our SRADs are fatter and flatter. Why? We can have a larger concurrently executing workload on the same SRAD versus POWER9. And the reason why we can do better is we have more powerful cores and 12 of them housed together. Fatter. Flatter. We got so much more cache that migrates and communicates and accesses each other so much faster. This is what I mean by flatter. When you're flatter, means you got more cache. With faster access, you don't need to leave the SRAD as often to reach outside of the SRAD. Fatter and flatter. POWER9, aim to exploit the strengths of POWER9, a denser, deeper core, a fatter and flatter SRAD. We build our LPARs in tune to the capabilities of technology. Doesn't that make sense? Strategy 4. Oh, I'm going to finish. Some of you have seen this before. This is my assumed scale of design presentation. Scale is designed by its mindedness. See, we have small, medium, large, huge mindedness. This is about aligning the scales of it. Aligning the scales of access data to addressing pages and the page size and the size of processes and data and processes shared memory and the LPAR memory's concurrent need. Aligning it. What I mean by aligning it, small, small, small. Small access data. You access multi-gigabytes of access data in a day. What's access data? The amount of data that you read and write in a day. If you only have multi-gigabytes of access data, it's okay to access that data as 4 kilobyte pages inside the OS to small memories and small memory processes and small shared memory. This is small-minded. What do I call this? I call this a scale-out workload. I call it 32-bit assumption era software, and this is where our workloads were born into. That's why smaller LPARs, smaller workloads run so well. That was the starting assumption, just between 32 and 64 bits. Medium-minded, more access data. Well, if you got big data, you better use a larger page size. I make the analogy of Lake Superior. If you want to empty out Lake Superior and all you got is a teaspoon, you're going to be scooping a lot of teaspoons to empty out Lake Superior. If you want to empty out Lake Superior and instead of a teaspoon, you're using a bucket the size of Lake Tahoe, you're going to be, moving a whole lot more water with your scoop. The idea is bigger data, address and access that bigger data in bigger pages. 2, larger processes in memory, because a process holds data. The bigger is the process, the more it holds. Bigger shared memory to hold that data, and larger memories in the LPAR. You've got bigger access data, you better have more memory through everything. Multi-terabyte access data. Accessing 16 meg to large processes. So, say you've got 4 liters of data and maybe 2 liters of memory. About half the data could be in memory. Performance is great. But what if you've got 100 liters of data and only a liter of memory? All you're going to do is I/O all the time. What am I saying? Depending on how much data you read and write, you better have a proper amount of memory so you don't have to keep on reading in and out of the cache repeatedly to SAN storage. Okay? So we know that data is getting bigger. We need to be aware that when we get bigger data, we need more memory. And when we have more memory, we need to access that memory in larger page sizes. That's what I mean by aligning the scales. Multi-petabyte, 16 gig, huge concurrent need. This is beyond the realm of AIX. We don't play in this space. Those other operating systems do on Power, but not AIX. So we're not here yet. Addressing. Okay, we have multiple page size support, and you see that these 4 match to small, medium, large, huge, concurrent need, optimum size of data and processes in shared memory. If you got big data, you better have larger memory processes and shared memory. This is about alignment. Well, what's misalignment? That's misalignment. Accessing a hell of a lot of data in 4K pages of small memory, that is not, well, it works, but it's not, it's misaligned. How's about a little bit of access data to big pages and small, it works, but it's kind of wasteful in large page sizes and it's not really needed. What about that? Supersized data, maybe larger pages, but your memory processes are too small. It'll run. It's not going to run really well. That's what I mean by alignment. What are we? We're mostly that today. That's how we are mostly today. We just need to be aware of the concept of it. Bigger data, larger memory, larger access address to page lists. So aligning memory access data to page sizes to amount of memory in alignment, not out of alignment, okay? Joe, I finished 15 minutes early. What the hell's the matter with me?
Yeah, you must not have covered enough material.
I mean, this has got 277 slides. What more can I ask?
That's right.
Okay, to you, Tom, what questions were asked? What rocks were thrown?
Well, let's see, Tom. Are you coming off mute? Tom really took care of most of the questions there. There isn't a whole lot.
Oh, that means my...
Can I ask a question?
You sure can.
Thanks. So I have one outstanding question. We're chatting amongst ourselves and trying to figure out how using the IST OPO command in a non-AIX environment, is that available on SUSE and those environments, or how do we do some of these techniques when we're outside of AIX?
I don't know. I don't know Linux. I'm sorry. I don't even know what command you were talking about.
Sounds like a Google question. Because I looked at that.
Yeah,
I'm not sure either.
So my colleague can't seem to speak or type into the deal, so he's translating a command I'm not real familiar with too, so I thought it was an AIX command. So he's chatting to me now. If I can, it's LSTOPO. So does that ring a bell?
No.
It didn't with me.
No. Okay. Well, sorry, Hans. I'm not translating it well for you, but yeah. So I guess really the bottom line is all of these commands that you're able to do in AIX, are we able to, HANA is where everything's going in our shop, and so we're trying to bridge the gap of understanding from our AIX world and how we're going to manage these systems and workloads under a HANA environment. And it seems to me HANA is a whole new beast when it comes to workloads, because you can't keep your LPARs. If you use an LPAR, you may bare metal it within the confines of an SRAD, right? So it's going to span SRAD, it's going to span KEX, and all bets are off when you're trying to tune that beast. Yes?
Yes.
Correct?
I don't know
Okay.
what I don't know, but somebody bought Red Hat, and maybe I have access to those guys.
Yeah, well, so it's a little different with a Linux, because you're running Linux instead of AIX, so your commands are a little bit different. But if you're running it under PowerVM, if you're doing LPARs under PowerVM, then there's, I think, still a lot of similarities for how you're going to build your LPAR and what the hypervisor is, because it's the same hypervisor. Then what the hypervisor is doing with that LPAR, it will work the same with I think Linux as AIX LPAR. So Earl, wouldn't this in that same case with what the hypervisor is doing would be the same as a lot of the stuff you covered there?
Yeah, and the other question I was trying to get a handle on was I'm running a blank. The 24 core variant versus the 12 core. Yeah, 12 core variant, and I heard him say right out of the bucket that AIX is not supported on the 24 core. But again, in light of a HANA implementation, where if you can keep things either into an SRAD or more things, memory, you can keep more memory footprints into an SRAD and avoid crossing SRADs and ultimately avoid crossing KEX. A 24-core variant should help you do that in a large multi-terabyte HANA implementation, yes?
Well, and Earl, jump in and correct me if I'm wrong, or what I say wrong here, and Tom can too. But the 24-core variant is just the 12-core with split cores, right? So you're still running on the same processor chip. The same amount of memory is still available on that same processor chip. So you've added more physical cores, but all those cores are on the same hardware chip. So in that case, you're on the same SRAD. All right.
Okay. All right.
And whether the 24-core variant isn't necessarily an AIX or IBMI thing. All right. AIX and IBMI only run on what I'll call 4 cores. They don't run on the split cores. All right. Linux is the only operating system that runs on the split cores, but Tom Prokop corrected me in there because I thought only our LC models we could do the split core in, and Tom said we just announced this week, which I wasn't aware of, that we allow a split core version in the 980 as well. But you can run Linux, and I'm trying to think of the HANA implementations that I'm familiar with all run on are all running on the full core version. They're not using the split core, the LC. Our HANA version of the Power Systems, the H model, runs the full core version. Okay. So, and again, Tom maybe can correct me if I misstated that, but my understanding is that's the way that is right now. So you're running the 12 core or the full core version when you're running HANA, and at least in my experience for what I've seen so far.
Okay. All right. Well, that clears up a little. That I didn't realize. I thought it was a bigger chipset, and you had more cores and potentially more L2 RAM and things of that nature all included in there. If you don't, then you still have the problem of a large database crossing SRADs and KEX and that, and HANA is just, I'll have one LPAR that's gonna blow through at least a couple 3 KEX.
Oh, absolutely. And HANA will do that, and it's got a huge memory footprint, and so that memory, just alone, that memory was probably spreading over several KEX, right?
Yeah.
And if you go back and look at so like last year we did I did a February version of a webinar that was on POWER9, and I kind of explained here's what the split cores and here's how they're made and how they're put together and stuff, and you can see in that how we split the cores up. But it's the same processor chip, and they tweaks it differently, all right, to get the 24 core out of that.
To the third speaker, I added the yellow and the green. If you remove the yellow and green, you'll have the 24 core SMT 4 cores. You can see that these 2 cores share the same L2, L3.
Right.
Okay.
AIX, I believe, only runs on Power VM on this 12-core SMT8 variant because each core maps to a virtual CPU, and a virtual CPU usually maps to your software licenses and how many you buy. If the core is more powerful, you buy fewer licenses. That's all.
So when you go to the 24 variant, do you lose power at the core level, or are they all equal power levels, or are you splitting the core power in 2?
Yeah. So when this first came out, I asked Jeff Stukley, who is one of the chip designers, because we were talking about RPerfs, and I said, so what's the RPerf difference between a processor, whether it's the split core or the full core. And he said actually the ARPers are very similar. It's pretty much the same. Okay, so I'm going to go ahead and just take control here for a minute.
Oh, that's a good analogy, because now we're getting close to SAPs, and right. So ARPers, there's tables that I can read how many SAPs need how many ARPers, and that translates down. So you're kind of telling me that at the end of the day, it's not going to make enough difference to worry about whether we go with the 12 variant to the 24 variant. It's not going to make it's probably not worth the increase in price.
Yeah, so I would treat this maybe a little bit differently in that the 24. So Linux takes advantage of cores a little bit differently, and smaller cores actually work well for Linux. Okay, so in some cases, and I don't know this is the case for HANA necessarily, because as I said, most of the HANA runs on the full core. But when we do the bare metal, they split the cores because in a lot of cases Linux just takes advantage of the smaller cores better. But when you say are they the same, you can see here that there's this slice and this super slice here, and the reason they're kind of similar is that they put these units in here, and there's one per slice. So the arithmetic unit, the load store, and the vector scalar unit. So they've got enough engines in the core so that every time you do it, it's when you split it in the split core, each half core then gets those engines in, and that's why the cores become very similar, because they built in enough into the hardware so that when they split the core, it's got its own internals to make it a full core. But it'll only run SMT4.
Oh, okay. Well, that could be a disadvantage with HANA. Well, with a highly threaded HANA implementation, which we have one, that the more thread, it's just highly threaded, massively threaded. So SMT8 is recommended for that type of implementation. So again, another restriction that would make us not go there.
Right, and you're using fewer cores, and if it's any per core licensing, right, then you want to use those fewer cores. So you're using fewer cores, getting better threading, and you're getting better performance out of it.
That's good too. Okay. All right. Well, thanks for indulging my questions, and sorry I veered off of AIX, but for our shop, the direction for power is headed that direction, and AIX we have a lot of it, but SAP, it all supports SAP, and SAP's direction is to move towards the HANA Linux-based environments, and we're just trying to understand at Earl's level, how to measure the workloads under the covers, because that's what Earl does, woman in red. So I'd love Earl to dig deeper into that when he gets time, but I don't know when he's going to figure out how to get time to go study that part of the new paradigm. Okay, good. Thank you for answering all my questions.
Yep, thanks. Earl, did you have any last minute parting things to say?
I have to put a bigger show together next time.
Okay, so there was a couple questions, the 24-core specific for HANA, and absolutely not. The 24-core variant, the split cores on the LC models are not just for HANA. They're for basically a Linux, more of a bare metal. It doesn't use the IBM hypervisor. Other hypervisors run underneath that. So the 24 cores for just basically other Linux implementations. So nothing else from you, Earl? And Tom is just a ghost in the background answering questions. Thank you, Tom. Appreciate that. Earl, thanks so much for doing this. I know you changed things and put it together just for this longer webinar, which is different than what you usually present. So I appreciate that. And we'll just have to have you back to do the next in your series on this, because I know you have several of them in it.
Always ready, Joe.
All right. So again, and you guys, if you're able to get to TechU, you can go and spend a day. Actually, Earl's doing several sessions at TechU. You can go back there and spend lots of time. Make sure that you're careful. I always worry about people's heads exploding when they spend a whole day listening to Earl. And with that, thanks, everybody. thank you again, Earl and Tom, and have a nice end of your summer. And you'll see, I'll send out invites for next month's webinar in the next couple of weeks.